The reason you can hold anything at all is a single rule proposed by a 24-year-old in 1925. Remove it, and every atom in your body collapses to the size of its own nucleus. The periodic table vanishes. Chemistry ends. Two objects touching releases the energy of a nuclear detonation. That is not a thought experiment. That was proved mathematically in 1967. The man who discovered the rule also discovered something else, a calculation about empty space so broken it predicts a universe smaller than the distance to the moon. He looked at that number and buried it, took it out of his own textbook, never spoke about it publicly again. That calculation is still broken. 100 years later, nobody has fixed it. Tonight, I want to walk you slowly through the full story. From Pauli's fourth quantum number in 1925 to the spin statistics theorem that ties the solidity of matter to Einstein's relativity, to Dyson-Lenard's 1967 proof that without this rule, matter itself is catastrophically unstable, to Chandrasekhar on a steamship calculating the mass at which even the exclusion principle loses to gravity, to the vacuum energy catastrophe that remains the worst prediction in the history of physics. Let's get into it. Pick up a stone, hold it in your palm, squeeze it, push your thumb into it as hard as you can. It does not give, it does not compress, it does not collapse under the pressure of your hand into a point of vanishing size, releasing as it goes the energy of a nuclear weapon. It just sits there. Ordinary, solid, taking up space. In 1967, two physicists at the Institute for Advanced Study in Princeton proved mathematically that if you removed a single quantum mechanical rule from the equations, that is exactly what would happen. Not figuratively, not as an exaggeration for dramatic effect. Freeman, Dyson, and Dyson-Lenard published a proof in the Journal of Mathematical Physics, Volume 8, Issue 3, showing that without the Pauli Exclusion Principle, the assembly of any two macroscopic objects would release energy comparable to that of an atomic bomb. Every atom in the stone would shrink by a factor of roughly 10,000. The periodic table would vanish. Chemistry would cease. The stone, your hand, and everything you have ever touched would not exist in any form you would recognize. That proof has been checked, refined, and extended for nearly 60 years. Nobody has found a flaw. The stone in your hand is balanced on a single quantum mechanical constraint, and that constraint is the only thing standing between the world you live in and a universe of compressed, featureless, catastrophically unstable matter. And here is where the story gets uncomfortable. The proof that this constraint must hold, the proof that electrons have no choice but to obey it, requires Einstein's special relativity. The reason matter is solid traces back to the speed of light being the same in every reference frame. That was established by Pauli himself in 1940 in a theorem so deep that Richard Feynman declined to explain it, saying he could not find a way to make it elementary. But the same framework, the same relativistic quantum field theory that proves why the stone is solid, also makes a prediction about empty space, about the energy of the vacuum. And that prediction is off by 120 orders of magnitude from what we observe. It is the worst quantitative prediction in the history of physics. The man who discovered the exclusion principle, Wolfgang Pauli, computed that prediction in the 1920s, saw how absurd the answer was, and quietly removed it from his textbook. He never solved it. Nobody has. One half of his physics holds up every atom in your body. The other half is the most spectacularly broken calculation human beings have ever produced. Both come from the same equations. Both use the same mathematics. And 100 years later, nobody can explain why one works and the other does not. This is the story of the man who figured out why matter has size, what his discovery actually means when you follow it all the way down, and what he found at the bottom that he could not bring himself to say out loud. The question that should terrify you is not some abstract philosophical puzzle. It is a physics question with a specific, technical answer, and the answer is so strange and so deep that the man who first proposed it in 1925 spent the next 33 years of his life trying to understand what it actually meant. His name was Wolfgang Ernst Pauli, and he was born on April 25th, 1900, in Vienna, into a world that was about to come apart. His father, also called Wolfgang, was a professor of colloid chemistry at the University of Vienna, who had changed his surname from Paschalis to Pauli and converted from Judaism to Catholicism to ease his passage through Habsburg academic life. His godfather was Ernst Mach, the philosopher and physicist whose relentless critique of Newtonian absolute space had helped clear the ground on which Einstein built relativity. Pauli grew up with physics as a native language, the way other children grow up speaking German or French. By 18, he was studying under Arnold Sommerfeld in Munich, the great teacher whose seminar room would also produce Werner Heisenberg and Hans Bethe, and half the Nobel laureates of the next generation. Sommerfeld had a reputation for discipline. Students attended lectures for 3 years before they were permitted to attempt the doctoral examination. But he recognized almost immediately that Pauli was not an ordinary student. When Felix Klein asked Sommerfeld for a comprehensive review of Einstein's general theory of relativity for the Encyclopedia of Mathematical Sciences, Sommerfeld gave the assignment to his teenage pupil. The result was a 237-page monograph that Pauli completed before his 21st birthday. It was published as a standalone book 2 months after he received his doctorate. Einstein read it and said that no one studying this mature and grandly conceived work would believe the author was a man of 21. Max Born, who had Pauli as an assistant at Göttingen the following year, later wrote that since the time Pauli was his assistant, he knew he was a genius, comparable only to Einstein himself, and that as a scientist, Pauli was perhaps even greater than Einstein, but a completely different type of man. That different type of man had a tongue that could cut steel. His colleagues called him the scourge of God, Die Geisel Gottes, and the terrible Pauli, der fürchterliche Pauli, in a Faust parody staged at Bohr's Institute in Copenhagen in 1932. The young physicists cast Pauli as Mephistopheles. He signed his letters God's Whip. When a friend showed him the paper of a young physicist and asked for his opinion, Pauli looked at it and said sadly that it was not even wrong. Das ist nicht nur nicht richtig, es ist nicht einmal falsch. The phrase has since entered the English language as a piece of universal intellectual currency. Peter Woit titled his critique of string theory after it. The phrase encodes a piece of philosophy sharper than it sounds. There is a meaningful difference between an idea that is wrong, which can be corrected, and an idea so vague it does not even rise to the dignity of being wrong. But the same man who devastated the imprecise was also, in private, the person other physicists wanted to read their drafts, the person whose approval mattered most. At the banquet held in Princeton, when Pauli received the Nobel Prize in 1945, Einstein gave a speech that Pauli later described in a letter to Born as like the abdication of a king, installing him as a kind of elected son, as his successor. I am telling you this not because it is interesting background. I am telling you because the personality of the man is inseparable from the physics he did. The same ruthless demand for precision that made him terrifying in a seminar room is exactly what led him, at 24, to propose a principle so strange he could not even name the property it described. To understand what Pauli found, You need to see the wreck he was trying to salvage. By the early 1920s, atomic physics was a building whose foundations were cracking. Niels Bohr's 1913 model had explained the spectrum of hydrogen with elegant simplicity. Electrons orbited the nucleus in quantized circles, each orbit labeled by a single integer n, the principal quantum number. When an electron jumped from one orbit to another, a photon was emitted or absorbed. The frequencies matched the spectral lines. It worked beautifully for hydrogen. But hydrogen has one electron. The moment you moved to heavier atoms, things fell apart. Sommerfeld had introduced a second quantum number, L, to describe the shape of the orbit, elliptical rather than circular. A third quantum number, M, the magnetic quantum number, was needed to describe how spectral lines split when you put an atom in a magnetic field, a phenomenon called the Zeeman effect, discovered by Peter Zeeman in 1896. The splitting should have been simple. A classical electron orbiting a nucleus in a magnetic field should produce 3 evenly spaced spectral lines, the normal Zeeman effect. And some atoms did show that pattern. But others, most of them in fact, showed something far more complicated, with half-integer spacings and extra lines that had no business being there. This was called the anomalous Zeeman effect. And by 1922, it had become the single most frustrating problem in atomic physics. Pauli was obsessed with it. Walking through the streets of Copenhagen at night, he ran into an acquaintance who remarked that he looked unhappy. Pauli answered, "How can one look happy when he is thinking about the anomalous Zeeman effect?" The standard approach at the time was to blame the atomic core, the inner electrons. Bohr and others hypothesized that the core had its own angular momentum that coupled to the magnetic field and produced the extra splittings. Pauli did not buy it. He had become convinced, through months of careful analysis, that the anomalous behavior was a property of the valence electron itself, the outermost electron, not the core. In the autumn of 1924, he published a paper rejecting the core model and proposing instead what he called, in a phrase that deserves to be lingered over, eine eigentümliche klassisch nicht beschreibbare Art von Zweideutigkeit, a peculiar, classically non-describable kind of two-valuedness of the quantum theoretical properties of the valence electron. Read that again. Two-valuedness, a property that takes one of two discrete values, up or down, plus or minus, 1/2 or negative 1/2. Classically non-describable, it cannot be visualized as the rotation of a small ball, as a pointer in space, as anything in our mechanical vocabulary. It is something the electron has, but for which we have no classical analog. To Pauli's knowledge, this was the first time anyone had proposed that a quantum mechanical degree of freedom existed that had no classical counterpart whatsoever. He was walking, he later said, without the crutches of the correspondence principle. And then, in October of that same year, an English physicist named Edmund Stoner published a paper in the Philosophical Magazine that connected two things nobody had connected before. Stoner noticed that the number of electronic states you could observe in a magnetic field matched, in a systematic way, the number of electrons that filled the successive periods of the periodic table, 2 in the first period, 8 in the second, 18 in the third, 32 in the fourth. The famous sequence 2, 8, 18, 32. Pauli read Stoner's paper and the pieces fell into place. If the electron carried a fourth quantum number, the two-valuedness he had just proposed, and if you combined it with the 3 numbers already known, then every possible electronic state in an atom was specified by 4 numbers. And Pauli's leap, his immortal contribution, was a rule of staggering simplicity. No two electrons in an atom can share the same set of all four quantum numbers. That is the exclusion principle. He submitted the paper to Zeitschrift für Physik in December of 1924. It appeared in January 1925, volume 31, issue 1, pages 765 to 783. The title, translated from the German, is on the connection between the closing of electron groups in an atom and the complex structure of spectra. Pauli was 24 years old. Think about what this means. The reason hydrogen has one electron in the first shell, and helium has two, and then lithium starts a new shell, is not because there is some force pushing electrons outward. It is because the first shell has exactly two available quantum states, one spin up and one spin down. And once those are filled, the next electron has no choice. It cannot go where the others already are. It must go higher. The shells close because the states fill. The periodic table, that magnificent empirical achievement of 19th century chemistry, Mendeleev's great chart of the elements, was now revealed as a direct readout of four quantum numbers and a prohibition. Carbon bonds the way it does because of the exclusion principle. Oxygen is reactive because of the exclusion principle. Noble gases are inert because of the exclusion principle. The entire discipline of chemistry, every reaction, every molecule, every material property of every substance you have ever touched, traces back to the way electrons stack themselves under Pauli's rule. And Pauli knew, even as he wrote the paper, that he had not explained why the rule held. The final paragraph of the 1925 paper contains a sentence of remarkable honesty. The problem of the more profound foundation of the general rule about the occurrence of equivalent electrons in the atom will probably succeed only after a further deepening of the basic principles of quantum theory. He was saying, in effect, that he had found the rule, but not the reason. The rule worked. The rule explained everything. But why the rule existed, why nature enforced it, remained completely unknown. Now here is where the story takes a turn that should bother you, because it reveals something about how physics actually works as a human enterprise, and it is not flattering. In January of 1925, a few weeks before Pauli's paper appeared in print, a young German-American physicist named Ralph Kronig, then 20 years old and working as an assistant to Alfred Lander, had an idea. The two-valuedness that Pauli had identified, Kronig proposed, might correspond to a physical spinning of the electron about its own axis. The angular momentum of this rotation would have, by quantum mechanical fiat, only two possible orientations, up or down. This would explain the fourth quantum number. This would explain the anomalous Zeeman effect. This would give Pauli's abstract two-valuedness a concrete physical picture. Kronig brought the idea to Pauli. Pauli's reaction was devastating. The electron, he pointed out, was extraordinarily small for a sphere of the electron's classical radius, about 2.8 times 10 to the negative 15 meters. To produce the observed magnetic moment through rotation, its surface would have to be moving at roughly 10 times the speed of light. That was impossible. Special relativity, the very theory whose definitive review Pauli had written at 21, forbade it. The idea, Pauli told Kronig, was clever nonsense, a ganz witziger Einfall. Kronig, who was young and junior, and facing the most feared critic in physics, did not publish. 9 months later, in the autumn of 1925, two graduate students at the University of Leiden, Samuel Goudsmit, 23, and George Uhlenbeck, 24, independently came up with the same idea. They had the same moment of doubt. Hendrik Lorentz, the grand old man of Dutch physics, made the same objection Pauli had made about the impossible surface velocity. Goudsmit and Uhlenbeck wanted to withdraw their paper, but their advisor, Paul Ehrenfest, had already mailed it to Naturwissenschaften. He told them, with characteristic warmth, "You are young enough to be forgiven for your stupidity." And then something happened that rescued the spinning electron from the trash bin. In February 1926, the American physicist Llewellyn Thomas resolved the factor of 2 discrepancy in the hydrogen fine structure that had been the most damning objection to the spin picture. The discrepancy turned out to be a relativistic effect, a rotation of the electron's rest frame relative to the nucleus, now called Thomas precession, that emerges from the difference between the Galilean and Lorentz transformations. With the factor of 2 resolved, the numbers worked. Even Pauli surrendered. In a letter to Bohr, dated March 12, 1926, he announced his total capitulation, but he never accepted the picture of a spinning ball. He insisted, and was later vindicated by Dirac's equation, that the electron's spin is not a rotation in any classical sense. It is, in the strongest possible meaning of the phrase, a quantum mechanical property. You cannot build a classical model of it. The electron's surface is not moving. The electron does not have a surface. The two-valuedness is exactly what Pauli said it was in 1924. Classically non-describable. The irony here has a particular flavor that physicists relish but rarely discuss publicly. Pauli discovered the property. Pauli named it. Pauli built the exclusion principle around it. And Pauli, by the sheer force of his criticism, was the man who prevented its physical interpretation from being published when it was first proposed. The credit went to Goudsmit and Uhlenbeck, whose advisor refused to let them retract their paper. Kronig, who had been right and had been silenced, went on to a distinguished career in solid-state physics, but never received the Nobel. The Nobel Committee honored Pauli in 1945 for the exclusion principle, not for spin. Spin, as a concept, was never separately honored, and the man who proposed it first was discouraged from publishing by the man whose principle it explained. That pattern, outsider proposes uncomfortable truth. Establishment figure crushes it. Decades pass. Outsider is quietly vindicated, is not unique to this story. It has repeated itself across the entire history of quantum mechanics, and it is repeating itself right now in different corners of physics. The exclusion principle's history is one of the earliest and cleanest examples. In 1926, after Schrödinger's wave mechanics arrived, the exclusion principle acquired its modern mathematical form, and this form is worth understanding because it is where the depth really begins. If 2 electrons occupy a joint quantum state described by a wave function psi of x and y, then exchanging the labels of the 2 electrons, swapping particle 1 and particle 2, must reverse the sign of the wave function. Psi of x, y equals negative psi of y, x. This is called antisymmetry under exchange. The consequence is immediate and absolute. If x equals y, if the 2 electrons are in the same quantum state, then the wave function must equal its own negative. Psi of x, x equals negative psi of x, x. The only number that equals its own negative is 0. The state does not exist. Its probability is identically 0. 2 electrons in the same state is not unlikely, not suppressed, not penalized. It is mathematically forbidden. The amplitude is 0. From this antisymmetry came 2 of the great achievements of the new quantum mechanics. In 1926, Enrico Fermi and Paul Dirac independently worked out the statistical mechanics of antisymmetric particles. These particles, which we now call fermions in Fermi's honor, obey Fermi-Dirac statistics. Particles whose wave functions are symmetric under exchange, where swapping two particles does not change the sign. Obey Bose-Einstein statistics, worked out in 1924 by Satyendranath Bose and Albert Einstein. These are called bosons. Electrons are fermions. Protons are fermions. Neutrons are fermions. Photons are bosons. And here is the pattern that should catch your attention. All the particles that make up ordinary matter, the particles that have mass and take up space and build the world you live in, are fermions. All the particles that carry forces, photons, gluons, the W and Z bosons, are bosons. The particles that obey the exclusion principle are the particles of substance. The particles that do not obey it are the particles of interaction. That is not a coincidence. It is the spin statistics theorem, and it is where Einstein enters the story in a way nobody expected. In 1940, Wolfgang Pauli, now displaced from Europe and living at the Institute for Advanced Study in Princeton, submitted a paper to Physical Review. It was published on October 15th of that year, Volume 58, Issue 8, pages 716 to 722. The title once again is deceptively simple: The Connection Between Spin and Statistics. The paper proves that the connection between a particle's spin and the statistics it obeys is not an empirical accident. It is forced by the structure of relativistic quantum field theory. Particles with half-integer spin, 1/2, 3/2, 5/2, must be fermions, must obey the exclusion principle. There is no choice. Particles with integer spin, 0, 1, 2, must be bosons, must allow unlimited occupation of the same state. There is no choice there either. The connection is not a correlation. It is a theorem. The proof rests on three assumptions. The vacuum is the lowest energy state. Physical operations performed at points too far apart for light to travel between them cannot influence each other, a requirement called microcausality. And probabilities are non-negative. Every one of those assumptions seems obvious. They should be obvious. They are the bare minimum you need for physics to be physics. And yet, from those three things, combined with Lorentz invariance, the symmetry of physics under the transformations of special relativity, the entire spin statistics connection falls out. Here is the key physical insight. If you try to make a spin 1/2 field commute at space-like separation, the way a bosonic field does, then either positive energies are unbounded below, or the field operators fail to commute. The theory breaks. Conversely, if you try to make a spin 1 field anti-commute the way a fermionic field does, microcausality fails. Signals travel faster than light. Either way, the theory is sick. The only consistent assignment is the one nature actually uses. Half-integer spin goes with antisymmetry. Integer spin goes with symmetry. And Lorentz invariance, Einstein's special relativity, is absolutely essential to the proof. You cannot derive the spin statistics theorem in non-relativistic quantum mechanics. In Schrödinger's wave mechanics, there is no fundamental reason an electron has to be a fermion. You can write down a perfectly self-consistent theory of bosonic electrons obeying the Schrödinger equation. Nothing in the non-relativistic formalism forbids it. The exclusion principle in non-relativistic quantum mechanics is an additional postulate imposed by hand to match experiment. Bring in relativity, and the postulate becomes a theorem. Think about what that means. Think about it carefully. The reason atoms have size, the reason matter is solid, the reason chemistry exists, traces back not just to quantum mechanics, but to Einstein's special theory of relativity, the theory of the speed of light, the theory that says the laws of physics look the same in every inertial frame. The theory whose 237-page review Pauli had written at 21. Without Lorentz invariance, without the constancy of the speed of light, without the specific way that space and time transform into each other under changes of velocity, there is no proof that electrons must obey the exclusion principle. The reason your hand does not pass through the table, the reason the stone you are holding is solid, the reason your bones support your weight, all of this is, at bottom, a consequence of special relativity applied to quantum fields. Einstein is the hidden reason chemistry works, and that fact, which is published and well known among theoretical physicists, is almost never mentioned in any chemistry textbook, any popular science book, any high school or undergraduate course on the periodic table. You were never told, not because it is controversial, not because it is uncertain, but because the implication connects too many things that are normally taught in separate departments by people who do not talk to each other. And the full picture, when you assemble it, is strange enough to be uncomfortable. Pauli's own assistant, Marcus Fiers, had laid the mathematical groundwork in 1939. Julian Schwinger gave an alternative proof in 1950 based on time reversal invariance. Gerhard Ludus and Bruno Zumino gave proofs from axiomatic quantum field theory in 1958. Streeter and Weidmann wrote the definitive textbook treatment, PCT spin, and statistics and all that. The theorem is as well established as anything in physics. But here is the part that even physicists find unsettling. Nobody has ever produced an intuitive explanation of why it is true. Feynman, in the Feynman Lectures on Physics, Volume 3, Chapter 4, declined to derive it. He wrote that he could not find a way to explain it at the level he wanted. Ian Duck and E.C.G. Sudarshan, in their 1998 book, Pauli and the Spin Statistics Theorem, wrote that it is only a slight exaggeration to say that everyone knows the spin statistics theorem, but no one understands it. The connection between a particle's behavior under rotations and its behavior under exchange is proved. It is correct. It is one of the most consequential results in all of physics, and nobody can tell you, in plain language, why it is true. The theorem holds. The intuition is missing. The equations work. The understanding does not. That should bother you. It should bother you because the theorem is not a minor technical detail. It is the reason matter exists. And the fact that we can prove it is true, without being able to explain why it is true, suggests that we are operating at a level of physics where our usual tools of understanding, our pictures and analogies and mental models, have stopped working. We can still do the math. We just cannot see what the math means. And here is the forward reference that should keep you watching. The same relativistic quantum field theory framework that produces the spin statistics theorem, that proves why electrons must exclude, also produces something else. It produces a prediction about the energy of empty space. And that prediction does not add up. It does not add up by a margin so large that calling it a discrepancy is like calling the Pacific Ocean a puddle. We are going to get to that. But first, you need to see what happens when the exclusion principle is taken away. Because the world without it is not merely different from ours. It is a world that cannot exist. To understand how desperate the situation was in the early 1920s, you need to understand what the anomalous Zeeman effect actually looked like in the laboratory and why it drove an entire generation of physicists to the edge of despair. The normal Zeeman effect was understood. Put an atom in a magnetic field, and some of its spectral lines split into 3 components, evenly spaced, exactly as you would predict from a classical model of an electron orbiting a nucleus in a magnetic field. Lorentz had worked this out in 1897, and Zeeman shared the 1902 Nobel Prize with Lorentz for its discovery and explanation. But when you looked at heavier atoms, at the sodium doublet, for example, the splitting was not a clean triplet. It was a mess. The sodium D lines, the bright yellow lines you see when you burn sodium in a flame, split into 4 and 6 components respectively in a magnetic field. Other atoms showed even more complicated patterns. The spacings were not evenly distributed. Some of the components were at half-integer multiples of the expected spacing, which made no sense in any theory based on integer quantum numbers. Alfred Landé at Tübingen had developed a set of empirical rules, the Landé G-factors, that could predict the complicated splittings with remarkable accuracy. But the rules contained half-integer quantum numbers that had no justification in the existing theory. They worked. Nobody knew why they worked. Sommerfeld called the anomalous Zeeman effect the zoo of spectral lines. Bohr and his school at Copenhagen tried increasingly baroque models involving the angular momentum of the atomic core. None of them were consistent. Pauli's contribution was to cut through the baroque models with a principle of radical simplicity. Forget the core, forget the classical pictures. The electron itself has a property specified by 2 values, and this property, combined with the 3 known quantum numbers, gives you 4 quantum numbers per electron, and no 2 electrons in an atom can have the same 4. From that single rule, the entire zoo of spectral anomalies could be tamed. The anomalous Zeeman effect fell out. The periodic table fell out. The closing of electron shells fell out. It was not a model. It was a prohibition. And the prohibition was more fundamental than any model. The reaction in the physics community was mixed. Some, like Sommerfeld and Bohr, recognized immediately that Pauli had found something profound. Others were uneasy with a principle that seemed to be imposed from outside the theory rather than derived from it. The unease was justified. The exclusion principle, in 1925, was a rule without a reason. It told you what nature did, but not why nature did it. And that gap between the what and the why would take 15 years to begin to close and, in a sense, has never fully closed. The Kronig affair deserves more attention than it usually receives because it illuminates something important about how physics actually works. As a social enterprise, Ralph Kronig was not a crank. He was a talented young physicist, born in 1904 in Dresden, who had studied at Columbia University and was working with some of the best theorists in Europe. His proposal of electron spin was not a casual speculation. He had worked through the mathematical consequences and could show that a spinning electron would explain the anomalous Zeeman patterns, the doublet structure of alkali spectra, and the 4th quantum number that Pauli had just postulated. He brought the idea first to Landé, who encouraged him, and then to Pauli, who demolished him. Pauli's objection was specific and technically correct. If you model the electron as a sphere of classical radius and calculate the angular velocity needed to produce the observed magnetic moment, the surface speed exceeds the speed of light by about a factor of 10. This is a genuine problem for a classical model of spin. It is not a problem for the actual quantum mechanical property that we now call spin, because spin is not classical rotation. But in January 1925, nobody yet understood that distinction clearly. What happened next is the part that history rarely emphasizes. Kronig, after being dismissed by Pauli, also showed his work to Heisenberg and several other physicists. The reception was universally cold, not because the idea was wrong, but because Pauli had said it was wrong. And Pauli's judgment carried a weight that nobody in the younger generation had the standing to challenge. Kronig put the manuscript away. When Goudsmit and Uhlenbeck published the same idea 9 months later, they faced the same objection from Lorentz. The difference was that their advisor, Ehrenfest, had the seniority and the confidence to override the objection. You are young enough to be forgiven. That sentence saved the publication of electron spin and, by extension, set the stage for Dirac's equation, for quantum electrodynamics, for the entire modern theory of the electron. Kronig lived until 1995. He had a long career at the University of Groningen, made significant contributions to the theory of X-ray absorption and to the Kramers-Kronig relations, and was elected to the Royal Netherlands Academy. He was never bitter about the spin episode in any public statement, but the physics community's collective memory has acknowledged with quiet discomfort that Kronig was right and was silenced, and that the silencing was not the result of a deliberate conspiracy, but of the ordinary social dynamics of deference and authority. Pauli was the conscience of physics, and when the conscience said no, people listened. The lesson is not that Pauli was a villain. The lesson is that even the most rigorous and honest scientific culture can suppress a correct idea, not through malice, but through the weight of reputation. And the lesson applies far beyond the history of electron spin. Let me go deeper on what Chandrasekhar actually calculated on that steamship, because the physics is beautiful and the personal stakes are immense. Chandrasekhar had just graduated from Presidency College in Madras at the age of 19. He had been offered a scholarship to study at Cambridge under Ralph Fowler, who had recently written a paper showing that the dense matter in white dwarf stars could be explained by treating the electrons as a Fermi gas, a collection of fermions obeying quantum statistics. Fowler's calculation used non-relativistic quantum mechanics and showed that a white dwarf could reach a stable equilibrium where the electron degeneracy pressure balanced gravity. On the ship, Chandrasekhar asked what would happen if the electrons in the white dwarf were moving at speeds close to the speed of light. At the densities involved, of order 10 to the 6th grams per cubic centimeter, this was not a hypothetical question. The Fermi energy of the electrons in a sufficiently massive white dwarf would be comparable to the electron rest mass energy of 511 kilo-electron volts, meaning the electrons would be relativistic. The calculation he performed on the steamship, using the relativistic generalization of the Fermi-Dirac equation of state, showed that the pressure-density relationship changes in a crucial way at relativistic speeds. In the non-relativistic case, pressure scales as density to the 5/3 power. In the ultra-relativistic case, it scales as density to the 4/3 power. The exponent drops. And that drop in the exponent means that for a sufficiently massive star, the degeneracy pressure cannot increase fast enough to counteract the gravitational force. There is a maximum mass. The value Chandrasekhar calculated on the ship was approximately 1.44 solar masses, a number that has been refined slightly over the decades but remains essentially correct. Above that mass, the white dwarf contracts. Electrons are forced to merge with protons to form neutrons. Neutrinos are released in a burst that can blow off the outer layers of the star, and the core collapses to a neutron star or, if massive enough, to a black hole. What Chandrasekhar had found at age 19 on the deck of a steamship crossing the Indian Ocean was that the exclusion principle has a ceiling. There is a mass above which it loses. Gravity wins. The fermions are overwhelmed. The stars collapse. He presented this result at Cambridge and received encouragement from some quarters. Fowler was intrigued. R.H. Fowler was supportive. Edmund Whittaker, the great Edinburgh mathematician, was impressed. But the shadow of Eddington loomed. Eddington was not merely the most prominent astrophysicist in Britain. He was the most prominent astrophysicist in the world. His 1919 eclipse expedition had made Einstein famous. His books on stellar structure and relativity were standard texts. His word in British astrophysics was close to law. Eddington's objection to Chandrasekhar was not based on a mathematical error. Chandrasekhar's mathematics was correct, and everyone knew it. Eddington's objection was philosophical. He could not accept that a star could collapse indefinitely. He could not accept that there was no final stable state. He called the result a reductio ad absurdum and argued that some unknown physical mechanism must intervene to prevent the collapse. No such mechanism was ever found. The collapse is real. Type AEA supernova. The standard candles that Perlmutter and Ries and Schmidt used to discover the accelerating expansion of the universe in 1998 are white dwarfs that exceed the Chandrasekhar limit by accreting matter from a companion star. The discovery that won the 2011 Nobel Prize in Physics, the discovery of dark energy, depends directly on Chandrasekhar's calculation being correct, and the man who tried to prevent that calculation from being accepted, the man who used his institutional authority to publicly humiliate a 24-year-old with correct mathematics, was never formally censured, never publicly contradicted by his peers at the time, and died in 1944, still believing he was right. Chandrasekhar waited nearly 50 years for the Nobel. The timeline of that wait is itself a measure of what institutional authority can do when it is wrong. I want to return to Pauli's vacuum energy calculation one more time, because there is a detail that is usually omitted, and that connects everything. The specific textbook in question is Pauli's article in the Handbuch der Physik, the great German language reference encyclopedia of physics. Pauli wrote the article on wave mechanics for the 1933 edition, and it was later revised and published in English as General Principles of Quantum Mechanics by Springer in 1980. The article went through several revisions during Pauli's lifetime, and it is in the changes between editions that the story of the vacuum energy calculation is preserved. In the 1933 edition, Pauli included a discussion of zero-point energy and its formal treatment. He noted, in a passage that Norbert Straumann has analyzed in detail, that it was more consistent for the radiation field not to introduce a zero-point energy of 1/2 h nu per degree of freedom. This is an extraordinary remark. Pauli is essentially saying that the zero-point energy of the electromagnetic field, which is a direct and unavoidable consequence of the commutation relations of quantum field theory, should be ignored on the grounds that its consequences are too severe. He was right that the consequences are too severe. He was also right that ignoring the zero-point energy is inconsistent with the formalism. The commutation relations require it. The Casimir effect, predicted by Hendrik Casimir in 1948 and confirmed experimentally by Steve Lamoureux at Los Alamos in 1997, demonstrates that vacuum zero-point energy has real, measurable physical effects. Two uncharged conducting plates placed close together in a vacuum experience an attractive force because the boundary conditions imposed by the plates restrict the allowed modes of the electromagnetic field between them, reducing the zero-point energy in the gap relative to the unrestricted vacuum outside. The force has been measured to percent level accuracy. The zero-point energy is real. It gravitates, and if you sum it up, the gravitational consequences are catastrophic. The Casimir effect proves that you cannot simply declare the vacuum energy to be zero. It is not zero. It has measurable physical effects. The question is not whether the vacuum has energy. The question is why it has so much less gravitational energy than it should. Pauli, in the 1920s, saw this problem clearly enough to compute the answer, and clearly enough to know the answer was absurd. He lacked, as we all still lack, any idea of what to do about it. So he made the only move available to a man of his temperament. He noted the inconsistency, removed the calculation from the published record, and moved on to problems he could solve. The rest of us are still stuck where Pauli left us. But before I tell you about the proof, there is something else about Pauli you need to understand, because it connects directly to why the exclusion principle is the way it is, and why Pauli spent his life circling around questions that other physicists considered settled. Among the experimental physicists of Pauli's generation, particularly in Hamburg and Göttingen and Zurich, a peculiar superstition circulated. The story went that complex laboratory equipment failed in Pauli's presence. Vacuum pumps leaked. Oscilloscopes died. Expensive measuring apparatus stopped working without apparent cause. The phenomenon was called, with mock formality, the Pauli effect, and it was described by some as a second Pauli Exclusion Principle, according to which a functioning experimental device and Wolfgang Pauli could not occupy the same room. The most famous anecdote was preserved by George Gamow. James Franck, the director of the Physics Institute in Göttingen, wrote to Pauli in Zurich to report that an expensive piece of equipment had broken down inexplicably. He added, as a joke, that at least this time Pauli was innocent, since he was hundreds of miles away. It then emerged that Pauli, on that very afternoon, had been changing trains at the Göttingen railway station on his way back to Zurich. The breakdown had occurred at almost exactly the moment of his transit through the town. Otto Stern, the Nobel laureate experimentalist, reportedly banned Pauli from his laboratory in Hamburg despite their close friendship. In February 1950, while Pauli was visiting the Institute for Advanced Study in Princeton, the cyclotron at the Princeton University Physics Department, a machine with a 50-ton magnet, caught fire and burned for more than 6 hours. The episode that disturbed Pauli personally was not a laboratory failure. On April 24, 1948, at the inaugural ceremony of the C.G. Jung Institute in Zurich, as Pauli entered the room, a Chinese vase fell from a shelf without any obvious cause, shattered on the floor, and released a puddle of water. Pauli wrote to Jung about that comical Pauli effect of the overturned vase, and the incident led him deeper into his investigation of what he and Jung were calling synchronicity, the hypothesis that meaningful coincidences reflected in a causal connecting principle, operating alongside causality. You might think this is a digression. It is not. The man who demanded mathematical rigor above all else, who would not accept an idea that was not even wrong, who crushed Kronig's correct proposal of electron spin because it violated special relativity by a factor of 10. This same man was willing to entertain the idea that his own unconscious mind could influence physical reality at a distance. He did not adopt this position carelessly. He adopted it because he had spent decades working at the boundary where physics meets something it cannot explain. And the exclusion principle was one of those boundaries, a principle with no intuitive explanation, no classical analog, no deeper foundation that anyone could articulate. A principle that simply was. Pauli's engagement with Jung was not a lapse in his scientific judgment. It was an extension of the same question that had driven his entire career. Why does this rule hold? What is the pattern underneath? And when the physics gave him a theorem without an explanation, he looked elsewhere for the explanation, not because he had abandoned rigor, but because he had pushed rigor to its limit and found the limit. I am telling you this because the exclusion principle is not just a line in a chemistry textbook. It is a fact about the universe so deep so fundamental, and so resistant to intuitive understanding that the man who discovered it spent the last 26 years of his life in correspondence with a psychoanalyst trying to figure out what it meant, and the rest of physics has not done much better. Now I need to take you through the actual mechanics of what happens when you remove the exclusion principle, because the Dyson-Lenard result is often stated in summary form without the physical picture, and the physical picture is what makes it terrifying. Imagine you could turn off the exclusion principle. Imagine the constraint that no two electrons can share a quantum state simply cease to operate. What would happen? The first thing is that every electron in every atom would fall to the lowest energy state. In hydrogen, nothing changes, because hydrogen only has one electron. But in helium, both electrons would now occupy the 1s orbital with the same spin. In lithium, all 3 electrons would pack into the ground state. In carbon, all 6. In iron, all 26. In uranium, all 92. With all electrons in the ground state, the radius of the electron cloud would shrink dramatically. In the normal atom, the outermost electrons are far from the nucleus because they have been forced into higher shells by the exclusion principle. Remove that forcing and they all collapse inward. The effective radius of the atom would scale as 1 over z, the atomic number, rather than the roughly constant or slowly varying radius we observe in real atoms. A uranium atom, which in our world has a radius of about 175 picometers, would shrink to roughly 2 picometers. That is smaller than the radius of the first Bohr orbit of hydrogen. Uranium would be smaller than hydrogen. And here is where it gets worse. The energy released by this collapse would be enormous. Each electron falling from a higher shell to the ground state releases energy proportional to z squared times the binding energy scale. For heavy atoms, this is not a trivial amount. And in bulk matter, the collapse would be even more extreme, because the electrons from neighboring atoms would also crowd together. And without the kinetic energy barrier created by the exclusion principle, the electrostatic energy would drive a runaway compression. Dyson and Lenard's calculation showed that the ground state energy of n-charged particles without fermionic statistic scales has n to the 7/5, not n. The energy per particle grows with the number of particles. For a mole of atoms, roughly 6 times 10 to the 23rd particles, the energy stored in the collapsed state would be beyond anything in our ordinary experience. Bringing 2 such objects together would not produce a small spark or a modest chemical explosion. It would release energy densities comparable to nuclear processes, because the matter would have collapsed to nuclear scale densities. The periodic table in this world would not exist. Every atom, regardless of its atomic number, would have essentially the same structure. All electrons in the ground state, a tiny dense ball of negative charge surrounding the nucleus. There would be no valence electrons, no outer shell chemistry, no reason for carbon to bond differently from nitrogen or oxygen or gold. Carbon would not form 4 bonds. Oxygen would not form 2. Nothing would form bonds in the way we understand bonding, because bonding depends on the sharing and rearrangement of outer shell electrons, and without the exclusion principle, there are no outer shells. Without the periodic table, there is no chemistry. Without chemistry, there are no molecules. Without molecules, there are no proteins, no DNA, no water, no lipid membranes, no cellular machinery of any kind. Biology is, at bottom, an expression of the chemistry of carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. And that chemistry depends entirely on the way those elements arrange their electrons in shells. Remove the shells and you remove biology. not as a matter of detail, but as a matter of category. There is no version of life that could exist in a universe without the exclusion principle, because there is no version of chemistry. And beyond chemistry, the mechanical properties of every material you have ever encountered depend on the exclusion principle. Metals conduct electricity because their outer electrons are delocalized across a lattice of positive ions, forming a Fermi sea, a collection of electrons obeying Fermi Dirac statistics, in which the highest occupied state, the Fermi energy, determines the conductivity. Without the exclusion principle, there is no Fermi sea, there are no bands, there is no distinction between conductors and insulators. The entire edifice of solid-state physics, the physics of semiconductors and superconductors and transistors, and every electronic device you have ever used, depends on the exclusion principle. The exclusion principle is not one fact among many about the quantum world. It is the load-bearing wall. Remove it, and everything else collapses. Not figuratively, literally. There is a quote from Pauli that appears in several sources, attributed to different occasions, but consistent in its content. God made the bulk, surfaces were invented by the devil. The quote is about condensed matter physics, about the fact that the behavior of the interior of a material is relatively straightforward, while the behavior of surfaces and interfaces is fiendishly complicated. But I think the quote carries a deeper resonance that Pauli may not have intended, or may have intended precisely. The bulk of the world, the solid, tangible matter that occupies space and resists compression, exists because of the exclusion principle. It is made by the deepest rules of quantum field theory, by the spin statistics connection, by the marriage of quantum mechanics and special relativity. That is the bulk. That is the thing God made. If you accept Pauli's metaphor, the surface of the world, the boundary where matter meets empty space, is where the trouble starts. Because at that boundary, the physics that works perfectly for matter meets the physics that does not work at all for the vacuum. The same equations, the same fields, the same framework, but the answers on one side are right, and the answers on the other side are wrong by 120 orders of magnitude. Pauli said God made the bulk. He did not say who made the vacuum. Perhaps that was the question he wanted to ask in room 137. Perhaps that is the question the devil would have answered. Let me now do something that the formal papers and textbooks do not do. Let me trace the chain from start to finish, from the stone in your hand to the cosmic embarrassment, and show you that it is one chain, not two. You hold a stone. The stone is made of atoms. The atoms have size because of the exclusion principle. The exclusion principle says no two electrons can share a quantum state. The reason the exclusion principle must hold is the spin statistics theorem. The spin statistics theorem says that half-integer spin particles must be fermions. The proof of the spin statistics theorem requires Lorentz invariance, the symmetry of special relativity. Specifically, it requires microcausality, the requirement that no signal travels faster than light. Without microcausality, the proof fails, and there is no reason electrons have to obey the exclusion principle. So the chain is this: the speed of light is constant. Therefore, space-time has Lorentz symmetry. Therefore, quantum fields must respect microcausality. Therefore, spin half particles must be fermions. Therefore, electrons obey the exclusion principle. Therefore, atoms have shells. Therefore, the periodic table exists. Therefore, chemistry exists. Therefore, the stone exists. That is the matter side of the chain. It is beautiful and complete and verified by every experiment that has ever been performed on the properties of matter. Now follow the same chain in a different direction. Quantum fields have 0-point fluctuations. The vacuum, the lowest energy state of those fields, has a non-zero energy density. That energy density gravitates according to general relativity. If you sum the 0-point energies and compute the gravitational effect, the answer is a cosmological constant roughly 120 orders of magnitude larger than what is observed. The two chains start from the same place. They use the same mathematics. They invoke the same fields, the same quantum mechanics, the same relativity. But one chain leads to a prediction that is confirmed to exquisite precision, and the other leads to the worst prediction in history. This is not a small problem. This is not a technical loose end. This is a crack running through the foundations of the most successful physical theory ever constructed. The same framework is spectacularly right and spectacularly wrong simultaneously. And the thing it is right about and the thing it is wrong about are not separate topics. They are the same topic. They are the quantum vacuum. The exclusion principle is a property of quantum fields. The vacuum energy catastrophe is a property of quantum fields. They are two faces of the same structure. And that, I think, is why this story matters beyond physics. Because it means that the most fundamental thing we know about why ordinary matter exists, the thing that explains why you can hold a stone, is connected by a direct logical chain to the most embarrassing failure in the history of quantitative science. The stone works. The space around it does not. And the explanation for both is the same physics. Pauli saw both ends of this chain before anyone else. He proposed the exclusion principle in 1925. He computed the vacuum energy catastrophe in the late 1920s. He proved the spin statistics theorem in 1940. And he spent the last decades of his life looking for the principle that would unify all of it. The pattern underneath the patterns. The thing that would explain why one half of the calculation works and the other does not. He did not find it. Nobody has. The stone still sits in your hand. The vacuum around it is still broken. And the connection between them is still the same set of equations, the same quantum fields, the same speed of light, the same 24-year-old's rule about 4 quantum numbers, and the prohibition that makes the world thick enough to hold. On October 31st, 1931, the Royal Netherlands Academy of Arts and Sciences awarded Wolfgang Pauli the Lorentz Medal. The physicist giving the laudation was Paul Ehrenfest, the brilliant, melancholic theorist at Leiden who had nicknamed Pauli the Scourge of God, and who had saved the spin paper from Goudsmit and Uhlenbeck's attempt to withdraw it. Ehrenfest had written ahead to Pauli, asking him to wear a formal black suit. Pauli replied by postcard from Zurich on October 26th. Dear Ehrenfest, just now I ordered a new black suit at my tailor's, but I shall only put it on at Amsterdam. If you promise me to thank me in public, in your official address at the Academy, for not having saved myself the trouble of going to the tailor. Ehrenfest, who understood theatre as well as he understood thermodynamics, complied. His speech at the ceremony, remembered in detail by Hendrik Casimir, who was watching from the balcony, contained a passage that has since become the single most quoted statement of what the exclusion principle actually does. We take a piece of metal or a stone, Ehrenfest said. When we think about it, we are astonished that this quantity of matter should occupy so large a volume. For the attraction of the 82 positive units of charge of the lead atomic nucleus is so powerful, many more of the 82 electrons could come together on the inner orbits before their mutual repulsion gets too large. What then prevents the atom from making itself smaller in that way? Answer: only the Pauli principle. No two electrons in the same quantum state. Therefore the atoms so unnecessarily thick. Therefore the stone, the piece of metal, so voluminous, you will have to concede, Herr Pauli, by partially waiving your exclusion principle, you might free us from many worries of daily life. For instance, from the traffic problem in our streets. And then, Ehrenfest ad-libbed, and how one might also considerably reduce the expenditure for a beautiful new, formal black suit. Casimir remembered Pauli's grin, and the increase in the amplitude of his characteristic rocking. Pauli rocked in his chair like a metronome during lectures and seminars, a physical tick that colleagues could observe from across the room, and that seemed to accelerate when the physics got more interesting. Ehrenfest's question is the right question, and it cuts deeper than it sounds at first. If the 82 electrons of a lead atom could all pile into the lowest 1s orbital, the atom would shrink enormously. The radius would scale roughly as 1 over z, the atomic number, rather than the actual scale set by shell filling. Lead, which has an actual atomic radius of about 175 picometers, would shrink to a few tens of femtometers. That is the scale of the atomic nucleus. Bulk lead, which has a density of about 11 grams per cubic centimeter, would instead have a density on the order of 10 to the 14th grams per cubic centimeter. That is the density of nuclear matter. Two such collapsed lead pieces brought into contact would not gently touch. They would release energy comparable to nuclear fusion. That is what Ehrenfest was really asking about, even if the full calculation had not yet been done. The question hovered in the physics literature for 36 years, understood qualitatively, never proved rigorously, until two men at the Institute for Advanced Study decided to settle it. Freeman John Dyson was born in Crowthorne, Berkshire, England, on December 15th, 1923. There is a strange symmetry in that date. Pauli would die on December 15th, 1958, exactly 35 years later to the day. Dyson grew up calculating. He took a mathematics degree at Trinity College, Cambridge, in 1945 after wartime service with the Royal Air Force, where he had done operational research on bombing patterns. He arrived at Cornell in 1947 on a Commonwealth Fellowship to study under Hans Bethe, and within months he found himself in the middle of the greatest theoretical breakthrough of the post-war era. Richard Feynman, at Cornell, was assembling his diagrammatic method for quantum electrodynamics. Julian Swinger, at Harvard, was working out his own operator formalism. Sin Ichiro Tomonaga in Tokyo had independently produced a third version by the summer of 1948. There were three distinct mathematical approaches to QED, all giving the same numbers to extraordinary precision. Nobody had proved they were the same theory. Dyson took a Greyhound bus from Cleveland to Albuquerque with Feynman in the summer of 1948 and used the hours on the road to interrogate Feynman about how the diagrams actually worked. He then attended a summer course Schwinner gave at the University of Michigan. On another long bus ride in the fall, the unification crystallized. He published the result in February 1949 in Physical Review as the radiation theories of Tomonaga, Schwinger, and Feynman, demonstrating the mathematical equivalence of all three formulations. J. Robert Oppenheimer, who had been skeptical of Feynman's pictures, was persuaded by Dyson's proof and offered him, in 1953, a lifetime appointment at the Institute for Advanced Study. For proving me wrong, Oppenheimer reportedly explained, Dyson never received a doctorate. He never needed one. He ranged across physics like a man who had decided that intellectual boundaries were a bureaucratic artifact. Random matrix theory, ferromagnets, nuclear reactor design, the Project Orion nuclear pulse spaceship, number theory, the search for extraterrestrial intelligence. He became, in Edward Witten's phrase, an unusual visionary. In the mid-1960s, Dyson turned his attention to an old problem that everyone assumed was finished. Chandrasekhar, a Hungarian-born mathematical physicist, born July 18, 1927, in Balmazújváros, who had emigrated to the United States in 1947 and studied at the University of Iowa, posed to Dyson the question that Ehrenfest had asked poetically, but that nobody had answered rigorously. Can we prove that matter is stable? The question sounds strange until you think about what it actually means. Classical electrostatics says that a positive charge and a negative charge attract each other with infinite energy as their separation goes to zero. In a classical world, electrons should spiral into nuclei. They do not, because of quantum mechanics, specifically because the uncertainty principle creates a kinetic energy cost for confining an electron to a small region. But even with quantum mechanics, is the total energy of a system of n-charged particles bounded below by a constant times n. Can you guarantee that no matter how many particles you assemble, the energy per particle stays finite, that the system does not implode? Michael Fisher and David Ruel had formalized this question in 1966 and had even put up a bottle of wine for the proof. The property they were asking about is called thermodynamic stability, or stability of matter in the second kind. Without it, a world cannot have thermodynamics. Without it, combining two objects does not give you a bigger object. It gives you an explosion. Dyson and Lenard worked at the Institute for Advanced Study through 1965 and 1966. Their paper, Stability of Matter I, was submitted to the Journal of Mathematical Physics on October 3, 1966, and appeared in March 1967 in Volume 8, Issue 3, pages 423 to 434. A second part appeared in 1968. The proof was, in Witten's assessment, one of the most advanced pieces of hard mathematical analysis up to that time. They got the bottle of wine. What Dyson and Lenard actually proved has two sides, and both sides matter. On the positive side, they proved that for a system of n particles belonging to a fixed number of fermion species, all interacting through Coulomb forces, the total ground state energy is bounded below by a constant times n. Energy scales linearly with particle number. This means ordinary matter, made of fermionic electrons and protons and neutrons, is thermodynamically stable. Bring two stones together, and the total energy is, to leading order, the sum of the energies of the two separate stones. The stones touch, they do not explode, they do not implode, they do not release nuclear scale energy. The exclusion principle, working through the kinetic energy cost of forcing fermions into higher momentum states, holds everything up. On the negative side, they proved that without the exclusion principle, the story is catastrophically different. If you remove the fermionic constraint, if you imagine a world of bosonic electrons that can all pile into the same quantum state, the ground state energy scales not as n, but as n to the 7/5. The energy per particle grows with the number of particles. More particles means more binding energy per particle. Volume decreases with particle number. Matter, in this hypothetical world, gets denser as it grows. Dyson summarized the consequences in a passage that has been quoted in every major review of the subject sense. We show that not only individual atoms, but matter in bulk would collapse into a condensed, high-density phase. The assembly of any two macroscopic objects would release energy comparable to that of an atomic bomb. And that description understates the case. N to the 7/5 for n of order Avogadro's number, 6 times 10 to the 23rd, is not comparable to an atomic bomb. It is many orders of magnitude beyond any conventional nuclear release. The world Dyson is describing is one in which macroscopic matter cannot exist at all, because any sufficiently large collection of particles would collapse into an exotic high-density state long before reaching visible size. There would be no stones, there would be no hands to hold them. There would be no chemistry, no biology, no periodic table, no molecules, no atoms in any form you would recognize. The universe without the exclusion principle is not a different version of our universe. It is an entirely different category of physical system. And here is the part that most textbooks skip entirely. The reason the exclusion principle holds matter up is not what you were probably told. You were probably told, if you took chemistry, that atoms do not collapse because electrons repel each other. Negatively charged electrons push each other apart, and this repulsion prevents them from all falling into the nucleus. That is wrong. Dyson-Lenard proved that Coulomb repulsion alone, without the exclusion principle, does not prevent collapse. The classical electrostatic repulsion between electrons is not strong enough to overcome the attraction to the nucleus when you have enough particles. What holds matter up is not a force between electrons. It is a constraint on the form of the wave function. The exclusion principle creates what is called degeneracy pressure or Pauli pressure. When fermions are squeezed into a smaller volume, the uncertainty principle forces them into higher and higher momentum states, because the lower states are already occupied. This costs kinetic energy. The tighter you squeeze, the more kinetic energy you pay. The resistance you feel when you push on a solid object, the normal force of a tabletop, the hardness of a diamond. All of this is ultimately the kinetic energy cost of trying to compress a system of fermions into a smaller region. You are not feeling electron-electron repulsion. You are feeling the anti-symmetry of the wave function. This was made rigorous in 1975 when Elliott Lieb at Princeton and Walter Thirring at Vienna published their landmark paper, Bound for the Kinetic Energy of Fermions, which proves the stability of matter in Physical Review Letters, Volume 35, page 687. The Lieb-Thirring inequality is a many-body uncertainty principle. It says that the total kinetic energy of n fermions is bounded below by an integral involving the 5/3 power of the local electron density. This inequality is the mathematical incarnation of what you feel when you push on a stone. The stone pushes back because the electrons inside it are fermions. The Lieb-Thirring proof is far shorter than Dyson-Lenard's, gives far tighter energy bounds, and is built around a connection to Thomas Fermi theory, a model of the atom developed independently by Llewellyn Thomas and Enrico Fermi in 1927, in which the electrons are treated as a continuous fluid. Lieb and Thirring proved that Thomas Fermi theory provides an asymptotic lower bound on the true energy for large atoms, and that Thomas Fermi atoms do not bind into molecules, a result due to Edward Teller. From this, they derived the linear in N stability with sharp constants. The modern reference is Lieb and Robert Seiringer's 2010 monograph, The Stability of Matter in Quantum Mechanics, published by Cambridge University Press. The program has been extended to relativistic kinetic energies, to matter in magnetic fields, and to matter treated with the full Dirac equation. The result is robust. Matter is stable because electrons are fermions. Remove that constraint, and everything falls apart. But the exclusion principle does not only explain why your stone is solid, it explains why certain stars exist, and it explains why, above a critical mass, they cannot. When a star like the Sun exhausts its nuclear fuel, The core can no longer generate enough thermal pressure to support itself against gravity. It contracts. In stars below a certain mass, the contraction is halted not by heat, but by electron degeneracy pressure. The same exclusion principle-driven kinetic energy resistance that makes your stone solid, operating now at densities of 1,000,000 grams per cubic centimeter, holds the stellar remnant up. This is a white dwarf. It is an exclusion principle object. Sirius B, the companion of the brightest star in the night sky, is a white dwarf. It has roughly the mass of the Sun compressed into a volume the size of the Earth. Its density is about 1,000,000 times the density of water. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth. All of that mass is supported against gravitational collapse by the refusal of electrons to share quantum states. Without Pauli's principle, Sirius B would not exist as a stable object. It would have collapsed further into something denser, something stranger. In 1930, a 19-year-old Indian physicist named Subramanian Chandrasekhar was on a steamship from Bombay to Cambridge to begin graduate study. On the deck of the ship, with the Arabian Sea stretching to the horizon, he worked through a calculation that nobody had done before. Ralph Fowler at Cambridge had shown that electron degeneracy pressure could support a white dwarf, but Fowler had treated the electrons non-relativistically. Chandrasekhar realized that for sufficiently massive white dwarfs, the electrons would be moving at speeds close to the speed of light, and the equation of state would change. He found that there was a critical mass, approximately 1.44 times the mass of the Sun, above which electron degeneracy pressure could not hold. Above that limit, which now bears his name, the Chandrasekhar limit, a stellar remnant cannot be a white dwarf. The exclusion principle as applied to electrons is not strong enough to resist the gravitational force. The star must continue collapsing into something else. The implications were dramatic and immediate, and the response of the physics establishment was one of the ugliest episodes in 20th century science. On January 11th, 1935, Chandrasekhar, then a fellow of Trinity College, Cambridge, presented his calculation to a meeting of the Royal Astronomical Society in London. He was 24 years old. The night before, he had dined at high table at Trinity with Sir Arthur Eddington, the most prominent astrophysicist in Britain, the man who had confirmed Einstein's general relativity by observing the bending of starlight during the solar eclipse of 1919. Eddington told Chandrasekhar, in a friendly way, that he had asked the Society's secretary for extra time to speak, and Chandrasekhar took this as a sign of support. It was not. Eddington had arranged to give his own talk immediately after Chandrasekhar's, and he used it to publicly, scornfully, and from the untouchable authority of Britain's most senior astrophysicist, demolish Chandrasekhar's calculation. Eddington declared that there should be a law of nature to prevent a star from behaving in this absurd way. He rejected the relativistic treatment of degeneracy on what amounted to aesthetic grounds, arguing that it led to conclusions he found philosophically unacceptable. The audience, which included many of Britain's leading astronomers and physicists, did not rally to Chandrasekhar's defense. William McCrae later admitted to Chandrasekhar's biographer Kameshwar that Eddington's arguments were superficially satisfying, and that since they satisfied Eddington, he was content to let it go. The episode devastated Chandrasekhar. He left Britain for the United States in 1937, took a position at the University of Chicago, and spent the next 48 years building one of the most distinguished careers in the history of theoretical astrophysics. The Nobel Prize came in 1983, nearly half a century after Eddington tried to bury his work. The Chandrasekhar limit was confirmed. The stars do collapse. The exclusion principle does have a ceiling. Above the Chandrasekhar limit, if the collapsing core does not blow itself apart in a supernova, it becomes a neutron star, supported now by neutron degeneracy pressure. The exclusion principle applied to neutrons rather than electrons. The maximum mass for a neutron star, the Tolman-Oppenheimer-Volkoff limit, is roughly 2 to 3 solar masses. Above that, there is no known form of degeneracy pressure that can halt the collapse. The end point is a black hole. The structure of the cosmos, on the scale of stars, is, at every level, the exclusion principle wrestling with gravity. White dwarfs are where the principle wins. Neutron stars are where it wins more desperately, at higher densities. Black holes are where it loses. And the man who humiliated Chandrasekhar did so not because the physics was wrong. It was correct. He did it because the conclusion made him uncomfortable. That pattern, where an established figure attacks a correct result because the implication is disturbing, is the same pattern we saw with Kronig and Pauli and spin. It is the same pattern that recurs throughout the history of physics whenever a young person's calculation reveals something the older generation would rather not confront. The physics community is not always the dispassionate, truth-seeking enterprise it presents itself as. It is a human institution with all the human weaknesses that implies, and sometimes the most important discoveries are the ones that take the longest to be accepted, not because they are uncertain, but because they are uncomfortable. And now we have arrived at the part of this story that Pauli himself could not face. Remember the framework: relativistic quantum field theory, Lorentz invariance, the spin statistics theorem, the exclusion principle, the stability of matter. All of these are pieces of the same mathematical structure, and that structure works. It works spectacularly. It explains atoms, molecules, white dwarfs, neutron stars, the periodic table, chemistry, the hardness of diamonds, the fact that you can pick up a stone. But that same framework, that same relativistic quantum field theory, also says something about empty space. And what it says is a disaster. Every mode of a quantum field, every possible oscillation pattern, carries a zero-point energy. This is a fundamental consequence of the uncertainty principle applied to fields. Even in the vacuum, even in the lowest energy state, the fields fluctuate, and each fluctuation mode carries an energy of 1/2 h bar omega. If you sum these zero-point energies over all modes, you get a total vacuum energy density. And that density, if you take it seriously, is enormous. Pauli, in the 1920s, asked the obvious question: what would this vacuum energy do gravitationally? According to general relativity, energy is energy, and it gravitates. A non-zero vacuum energy density acts exactly like Einstein's cosmological constant lambda. It curves space. So Pauli did the calculation. He summed the zero-point energies of the electromagnetic field, cut off the sum at a high-energy scale corresponding to the classical electron radius, about 2.8 times 10 to the negative 15 meters, and asked how tightly the resulting energy density would curve the universe. The answer, as reported by Norbert Straumann, based on conversations with Pauli's assistants Charles Enns and Armin Thelling, was that the universe could not even reach to the moon. Think about that. The same quantum field theory that correctly predicts the magnetic moment of the electron to 11 decimal places. The same theory that explains the Lamb shift and the anomalous magnetic moment and the Casimir effect, when asked about the gravitational consequences of its own vacuum state, produces an answer so wrong that the observable universe, roughly 93 billion light-years across, would be compressed to a radius smaller than the distance from the Earth to the Moon. about 384,000 kilometers. Pauli looked at this number and did something unusual for a man who made his career by being more honest than anyone in the room. He backed away from it. He did not publish the calculation as a crisis. He did not ring alarm bells in his 1933 Handbuch der Physik article on wave mechanics. He included a remark that it was more consistent not to introduce a zero-point energy for the radiation field, effectively waving the problem away. And according to the legend that circulates in the theoretical physics community, he removed or de-emphasized the calculation in subsequent editions of his work because the answer was too uncomfortable. Wilhelm Lenz, his Hamburg colleague, had made a similar observation as early as 1926. The problem was known. It was not hidden, but it was ignored for decades because nobody had any idea what to do about it, and because the practical physics of quantum electrodynamics worked perfectly well as long as you agreed not to ask about the gravitational side. This worked until it didn't. In 1989, Steven Weinberg published a review article in Reviews of Modern Physics, Volume 61, Issue 1, Page 1, titled The Cosmological Constant Problem. Weinberg laid out, with his characteristic clarity, the full dimensions of the catastrophe. If you take quantum field theory at face value and compute the vacuum energy density by summing the zero-point energies of all known fields, cutting off the sum at the Planck scale, the energy at which gravity itself becomes quantum mechanical, you get a vacuum energy density that exceeds the observed value by approximately 120 orders of magnitude, by a factor of 10 to the 120th power. To give you a sense of what that number means, consider this. If you made an error of a factor of 10, you would be off by 1 order of magnitude. If you predicted something should weigh a kilogram, and it weighed 10 kilograms, that would be embarrassing, but understandable. An error of 10 orders of magnitude would mean predicting a kilogram and finding 10 billion kilograms. An error of 120 orders of magnitude is so vast that there is no analogy in ordinary experience that captures it. It is as if you predicted the distance from New York to Los Angeles and got an answer larger than the observable universe. Not by a little, by a factor of 10 to the 80 or so. This is the worst quantitative prediction in the history of physics. It is not a close competition. No other discrepancy in any field of science comes within 100 orders of magnitude of this one. And what made it particularly painful in 1989 when Weinberg wrote was that the observed value of the cosmological constant was, as far as anyone could tell, exactly zero. The universe appeared to have zero vacuum energy. There were elegant arguments involving supersymmetry or unknown cancellation mechanisms for why the answer might be exactly zero. A zero answer is the kind of answer a deep symmetry might enforce. It would not solve the theoretical problem. The theory still predicts a huge number, but at least it would suggest some mechanism forcing a clean cancellation. And then in 1998, the rug was pulled. 2 independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the High-Z Supernova Surge Team, led by Brian Schmidt and including Adam Rees, were systematically observing distant Type Ia supernovae, which had been calibrated into excellent standard candles. Both teams expected to measure how quickly the expansion of the universe was decelerating, breaking under the mutual gravitational attraction of all the matter in the cosmos. Both teams found the opposite. The distant supernovae were too faint. The expansion was not decelerating, it was accelerating. The universe was flying apart, faster and faster. The published papers were Rees et al., Astronomical Journal, Volume 116, page 1009, 1998, and Perlmutter et al., Astrophysical Journal, Volume 517, page 565, 1999. The Nobel Prize in Physics in 2011 went to Perlmutter, Schmidt, and Reyes. The observed acceleration was consistent with a small but non-zero cosmological constant. The value was tiny in any natural units, roughly 10 to the negative 122 in Planck units, but it was not zero. The cosmological constant problem was no longer the question of explaining why a quantum field theory prediction of enormous magnitude was cancelled to exactly zero. It was the question of explaining why it was cancelled to within an almost impossibly precise but not quite exact amount, with a residue that happened to be mysteriously close to the present-day matter density of the universe. Think about what that requires. The quantum field theory prediction and whatever cancellation mechanism exists must agree to 120 decimal places and then disagree at the 121st. That level of fine-tuning has no precedent anywhere in physics. It is not a problem that might have a simple answer. It is a problem that might not have an answer at all within our current framework. And this 120 order of magnitude discrepancy between what the vacuum should weigh and what it does weigh is the legacy of the calculation Pauli did in the 1920s and then stopped talking about. The man who explained why matter has size also stumbled onto the fact that empty space does not make sense. Both answers came from the same physics. Both use the same framework. One works. The other is the most spectacularly broken prediction in the history of human thought. There is no consensus solution. Supersymmetric cancellations were once hoped to help, but supersymmetric has not been found at the Large Hadron Collider despite decades of searching. Anthropic explanations on a multiverse landscape, an idea Weinberg himself explored, remain controversial and possibly untestable. Modifications of gravity at cosmological scales have been proposed, but face their own difficulties. The swampland conjecture, advanced in 2018, suggests that no consistent quantum theory of gravity can even accommodate a stable, positive, cosmological constant, which, if true, would mean the dark energy we observe is not a cosmological constant at all, but something else, something dynamical, something we do not yet understand. A century after Pauli's calculation, the problem is exactly where he left it. Unsolved, unresolved, open, and it comes from the same equations that explain why you can hold a stone. There is a thought experiment that physicists use to test whether someone truly understands the exclusion principle, and it goes like this. Take 2 electrons, put one on Earth and one on the Moon. They are separated by 384,000 kilometers of vacuum. According to the exclusion principle, these 2 electrons cannot occupy the same quantum state. But what does that mean when they are nearly 400,000 kilometers apart? The formal answer is that the 2-electron wave function must still be antisymmetric under exchange. If you wrote down the quantum state of the entire system, the product of the electron on Earth state and the electron on Moon state, you would have to antisymmetrize it. The wave function would be the difference of 2 terms, one with electron A on Earth and electron B on the Moon, and one with the label swapped. This antisymmetrization has measurable consequences when the electrons are close together, because it affects the overlap of their wave functions and therefore the probability distributions. But when the electrons are far apart, the overlap is exponentially small, and the antisymmetrization has no practical effect. So the exclusion principle does not in practice prevent an electron on the Moon from having the same quantum numbers as an electron on Earth. because the two electrons are in different locations and location is part of the quantum state. But the principle does apply, in a formal mathematical sense, to every electron in the universe simultaneously. The wave function of all the electrons in the universe, every single one, must be totally antisymmetric under the exchange of any pair. This is not an approximation. It is an exact requirement. The number of electrons in the observable universe is estimated at roughly 10 to the 80th power. The wave function that describes all of them must change sign whenever you swap any two. That is an astronomically complex constraint enforced across cosmological distances, with perfect fidelity at every instant. How do the electrons know? That is the wrong question, framed in the wrong language. But it captures something genuine about the strangeness. The electrons do not know, because there are not, in the deepest sense, individual electrons. There is one electron field. The excitations of that field are what we call electrons. And the antisymmetry is not something the excitations do. It is something the field is. The field is antisymmetric the way water is wet. It is not a property imposed from outside. It is the nature of the thing. But saying that does not remove the strangeness. It relocates it. Why is the electron field antisymmetric? Because of the spin statistics theorem. Why does the spin statistics theorem hold? Because of Lorentz invariance and microcausality. Why does microcausality hold? Because nothing travels faster than light. Why does nothing travel faster than light? At some point in this chain of whys, you hit the floor. You reach a level where the answer is either that is just how it is, or we do not know, and neither answer is satisfying. And the dissatisfaction is the point, the deepest features of the physical world, the features that determine whether matter can exist, and whether atoms can have size, and whether you can hold a stone, rest on foundations that we can describe with equations but cannot explain with understanding. Feynman said it best, as he often did, in a lecture at Caltech. He was talking about the relationship between the mathematical formalism of quantum mechanics and the ability to understand what it means. He said, "I think I can safely say that nobody understands quantum mechanics." He was not being modest. He was making a precise philosophical claim. We know the equations. We can solve the equations. We can predict the outcomes of experiments to extraordinary precision. But we do not understand, in the way that we understand levers and pulleys and planetary orbits, why the equations are the way they are. The exclusion principle sits squarely in this gap between prediction and understanding. We can predict its consequences to arbitrary precision. We cannot explain, at the level of physical intuition, why half-integer spin particles must be antisymmetric under exchange. And the fact that this unexplained principle is the single thing standing between ordinary matter and catastrophic collapse, between the periodic table and a featureless compressed soup, between you and non-existence, should give you a specific kind of vertigo that is different from the vertigo of astronomy or cosmology. The vertigo of astronomy is about scale. You feel small against the vastness of the universe. The vertigo of the exclusion principle is about fragility. You feel held up by something you cannot see and cannot explain, and the mathematical proof that you need it is sitting right next to the mathematical proof that the vacuum it operates in does not make sense. There is a phrase Pauli used in his Nobel lecture, delivered in Stockholm on December 13th, 1946. He was describing the exclusion principle and its relationship to the spin statistics theorem, and he said that the connection between spin and statistics was derived by combination of the claims of relativistic invariance and the properties of field quantization. He went on to say that, already in my original paper, I stressed the circumstance that I was unable to give a logical reason for the exclusion principle, or to deduce it from more general assumptions. I had always the feeling, and I still have it today, that this is a deficiency. A deficiency. The man who explained why matter has size, who won the Nobel Prize for it, who was called Einstein's successor, described his own greatest achievement as deficient because he could not explain why it was true. That level of intellectual honesty is rare in any field. In physics, where the culture tends toward confidence and the history is written by the victors, it is extraordinary. Pauli could have accepted the prize, given a gracious speech, and never mentioned the gap. Instead, he named it. He called it a deficiency, and then he spent the remaining 12 years of his life trying to fill it. Through the spin statistics theorem, through his correspondence with Jung, through his obsession with the fine structure constant, and through his haunted circling around the vacuum energy catastrophe. He failed, but the failure was not a personal failure. It was a failure of physics itself, a failure that persists, a failure that is now a century old and shows no sign of resolution. The stone in your hand does not know any of this. The stone is just a stone. It sits in your palm, solid and warm, held together by a principle that a 24-year-old proposed in a German-language journal in 1925, proved to be necessary by the same man at age 40 using Einstein's relativity, shown to guarantee the stability of bulk matter by Dyson-Lenard in 1967, and connected by a direct logical chain to the worst prediction in the history of science. The stone does not care about the prediction. The stone just is. And the reason it just is, the reason it can just be, is the most important and least understood fact in the whole of physics. There is one more layer to this, and it is the layer that sits underneath everything else. And it is the one that even physicists sometimes slide past, because it is so strange that engaging with it honestly requires letting go of your last comfortable assumption about how the world works. The exclusion principle requires that two electrons be truly identical. Not identical in the sense that they happen to have the same mass and charge and spin, the way two billiard balls might happen to be the same color and size. Identical in a deeper sense. Identical in the sense that the very labels we attach to them, electron 1 and electron 2, are meaningless. There is no fact of the matter about which electron is which. In classical physics, two particles can be identical in their intrinsic properties, but still distinguishable in principle, because you can track their trajectories. You can say, this is the electron I started with on the left, and that is the electron I started with on the right, and even if they are identical in every measurable property, the labels stick because you can follow the paths. In quantum mechanics, you cannot do this. The wave function of two electrons must be either symmetric or antisymmetric under the exchange of their labels, and all physical observables must be invariant under the relabeling. There is no measurement, not even in principle, that can tell you which electron is which. This is what makes the exchange interaction physically real. The energy of two electrons depends not just on their positions and momenta, but on the requirement that swapping their labels changes the sign of the wave function. For two electrons close together, the antisymmetry forces the spatial part of the wave function to behave in a way that either pushes the electrons apart or pulls them together, depending on the relative orientation of their spins. This is not a force in the classical sense. It has no force carrier. It is a consequence of the topology of the wave function, the mathematical structure that quantum mechanics assigns to systems of identical particles. The strength of covalent bonds, the directional bonding that makes carbon into diamond, the metallic bonding that makes copper conduct electricity, the magnetic ordering that makes iron a permanent magnet. All of these are manifestations of the exchange interaction, and the exchange interaction is the exclusion principle in motion. Richard Feynman, in his 1979 book QED, The Strange Theory of Light and Matter, gave what remains the simplest popular summary of what all of this means. All the atoms, more than 100 different kinds, are made up of a certain number of protons exchanging photons with the same number of electrons. The patterns in which they gather are complicated and offer an enormous variety of properties. Some are metals, some are insulators, some are gases, others are crystals. There are soft things, hard things, colored things, a terrific cornucopia of variety and excitement that comes from the exclusion principle and the repetition, again and again and again, of the three very simple actions. And in a parenthetical aside in the same passage, Feynman added the line that closes the case more starkly than any treatise. If the electrons in the world were unpolarized, all the atoms would have very similar properties. The electrons would all cluster together close to the nucleus of their own atom, and would not be easily attracted to other atoms to make chemical reactions. That is the world without the exclusion principle, stated by the man who could simplify anything. Atoms are tiny, all nearly identical, all nearly inert, impossibly dense. The periodic table is a one-line document. Chemistry does not happen. The world is a uniform, featureless, compressed soup of matter. And here is where the question gets uncomfortable in a way that I think has never been adequately addressed in any popular account. The exclusion principle says that no two identical fermions can share a quantum state. But what does it mean for particles to be identical in this absolute sense? Not identical as a practical matter, not identical because we cannot tell them apart with current instruments, but identical as a matter of fundamental law, so that the wave function is required to treat them as indistinguishable. The standard answer, the one a quantum field theory textbook will give you, is that there are not separate electrons at all. There is one electron field, a single quantum field spread across all of space, and the things we call electrons are excitations of that field. Individual electrons are like individual waves on a pond. You can count them. You can locate them, but they are not separate objects in the way that billiard balls are separate objects. They are patterns in a single underlying substance. The knowledge that one electron seems to have of every other electron, the ability of the exclusion principle to operate as if each electron knows what all the others are doing, is not a mysterious form of long-range communication. It is the structure of the field itself. That answer is technically correct and philosophically evasive in roughly equal measure, because the question it does not answer is why the field has this structure. Why antisymmetry? Why this particular topological constraint? And as we saw with the spin statistics theorem, the deepest answer available, because relativity demands it, is an answer that nobody has been able to explain intuitively, even after 85 years of trying. There is something about the woven togetherness of identical particles, the absolute indistinguishability that forces the exclusion principle. That sits at a level of physics we can operate at, but cannot see clearly. We can prove the theorems. We can derive the consequences. We can predict the properties of every element in the periodic table and the maximum mass of a white dwarf and the binding energy per nucleon of iron 56. What we cannot do is look at the spin statistics theorem and say, in plain language, oh, I see, that is why. That understanding has eluded every physicist who has tried, from Pauli to Feynman to Schwinger to Sudarshan. The stone in your hand is the output of a calculation we can perform but cannot fully understand, and the vacuum around it is the output of a calculation we can perform that does not work at all. I want to tell you how the story ends, But the story has a peculiar property. It does not end. It just gets stranger. Paul Ehrenfest, the man who asked the right question about why atoms are so fat, the man who saved the spin paper from Goudsmit and Uhlenbeck, the man whose voice at the Lorentz medal ceremony captured the deepest implication of the exclusion principle in ordinary language, did not live to see any of what followed. In May of 1931, 2 months before the ceremony, he had written to Bohr and Einstein and a handful of others a letter in which he said he had completely lost contact with theoretical physics, that he could not read anything anymore, and felt incompetent to have even the most modest grasp of what made sense in the flood of articles and books. Einstein wrote to the Leiden board pleading for Ehrenfest's workload to be reduced. On September 25, 1933, in Amsterdam, Ehrenfest fatally shot his 15-year-old son, Wasik, who had Down syndrome and was living at an institute for special needs children, and then killed himself. He was 53 years old. His Lorentz medal speech, with its passage about why Pauli's principle alone keeps stones from being the size of walnuts, has outlived almost everything else he wrote. I am telling you this not because it is interesting background. I am telling you because the human cost of operating at the frontier of physics is rarely spoken about, and Ehrenfest's death is one of the starkest examples of what that frontier can do to a person who takes it seriously. The questions these people were asking were not abstract puzzles. They were questions about the nature of reality, and the answers, when they came, were not always things a human mind could comfortably hold. Pauli, in the years after the spin statistics theorem, continued to be the conscience of physics. He corresponded with everyone. He criticized everything. He remained into his 50s the man other physicists sent their drafts to when they wanted to know if the work was any good. There is a story about the physicist Werner Heisenberg, who in the late 1950s became convinced he had found a unified field theory of elementary particles. He gave a talk on the theory at the Rochester Conference at CERN in 1958. Pauli was in the audience and was skeptical. After the talk, Pauli sent a letter to George Gamow containing a blank rectangle with the caption, "This is to show the world that I can paint like Titian. Only some technical details are missing." That was Pauli at 58, still sharp, still devastating, still convinced that the details mattered more than the vision. He also, in those final years, remained haunted by the number 137. The fine structure constant alpha is a dimensionless ratio that combines the charge of the electron, Planck's constant, and the speed of light into a single pure number. Because it is dimensionless, because it has no units, it should in principle be calculable from some deeper theory. Its reciprocal, 1 over alpha, is approximately 137. Not exactly. The precise value is closer to 137.036, but the proximity to an integer captivated a generation of physicists, from Eddington to Pauli to Feynman. Pauli once said, according to multiple sources, that when he died, his first question to the devil would be about the meaning of the fine structure constant. He also told the physicist Marcus Fers that a truly complete theory of physics would have to determine the value of the fine structure constant, and thus explain the atomistic structure of electricity, which is such an essential quality of all atomic sources of electric fields actually occurring in nature. He never found such a theory. Nobody has. In late November 1958, Pauli fell ill with abdominal pain. He was admitted to the Rotkreuz Hospital in Zurich when his assistant Charles Enns visited him. Pauli had a question. Did you see the room number? The number was 137. Pauli died in that room on December 15, 1958. At age 58, the diagnosis was pancreatic cancer, detected too late for treatment. He was buried in Zurich. His wife Franca, in 1960 and again in 1971, donated his personal archive, including his Nobel medal, to CERN. The Pauli effect, the superstition that experimental equipment failed in his presence, is usually told as a joke. Pauli himself treated it as something more. Throughout the 1930s and 40s, he had been in intensive correspondence with Carl Jung, the Swiss psychoanalyst, a collaboration that had begun in early 1932 after Pauli's mother committed suicide. His father remarried a woman Pauli detested, and his own brief first marriage to the cabaret dancer Käthe Deppner collapsed within a year. Had she taken a bullfighter, Pauli later said, I would have understood. But an ordinary chemist. Jung described Pauli at their first meeting as a case so severe it was as if the wind had blown over from the lunatic asylum. Over the following months, Pauli produced more than 1,000 recorded dreams, which Jung analyzed extensively. The dreams contained mandalas, alchemical imagery, the number 4, and most strikingly, a recurring image Pauli called the world clock, a cosmic structure of 2 interlocking circles that he took as a symbol of the unity underlying the apparent division between mind and matter. Jung's individual dream symbolism in relation to alchemy draws extensively on this material, with Pauli appearing only as an anonymous young man of distinguished scientific education. In 1952, Pauli and Jung jointly published an essay on synchronicity, the idea that meaningful coincidences reflect a deeper order connecting the physical and psychological. It is easy to dismiss this as a great physicist's late career detour into mysticism, but I think that reading misses what Pauli was actually doing. The same mind that demanded precision and rigor and called every sloppy idea not even wrong was also the mind that could not accept that the deepest regularities of physics, the exclusion principle, the fine structure constant, the spin statistics connection, were brute facts with no further explanation. He was looking for the pattern underneath the patterns, the rule behind the rules. He never found it. The search killed him, or at least it consumed the years that remained to him after the cancer had already begun. But the search itself was not irrational. The questions he was asking, why this value of the fine structure constant? Why this connection between spin and statistics? Why this vacuum energy catastrophe? Remain open questions in 21st century physics. He was ahead of his time in what he could not accept. And the things he could not accept are the things that still do not add up. Freeman Dyson died on February 28, 2020, at age 96. Chandrasekhar died on March 17, 2020, at age 92. Less than 3 weeks later, the two men who together proved why matter is stable left the world within days of each other. Dyson, who never received a doctorate, had publicly called the exclusion principle the most important fact in chemistry. He once visited Zurich and asked Pauli for an assessment of his work. Pauli's reply, as collected by Enns, was characteristically backhanded. Everyone wants to learn something from me. No one wants to teach me anything. I had hoped Dyson would do it, but he is only a mathematician. Chandrasekhar, who calculated the mass limit at which the exclusion principle fails against gravity, received the Nobel Prize in 1983 and continued working at the University of Chicago into his 80s. He died in 1995. Eddington's 1935 humiliation of him no longer features prominently in astrophysics curricula, but it shaped Chandrasekhar's scientific personality permanently, fixing in him a quiet almost obsessive thoroughness that his students recognized as the scar tissue of a public wound. Let me bring this back to the stone. You hold it in your hand, you feel its weight, which comes from the gravitational interaction with the Earth, the same gravity whose interaction with quantum fields has, since Pauli's 1920s calculation, refused to give a sensible answer. You feel its solidity, you push on it, and it pushes back. The reason it pushes back is not that the atoms inside are hard. The atoms are almost entirely empty space. The reason is that the electrons in those atoms are fermions. They obey the exclusion principle. They occupy distinct quantum states specified by 4 quantum numbers, the same 4 numbers Pauli identified in January of 1925. When you squeeze the stone, you are trying to confine those electrons into a smaller region. The uncertainty principle responds by forcing them into higher momentum states. The kinetic energy cost of that confinement is what you feel through your fingers as hardness. Lieb and Thering proved the lower bound on that kinetic energy in 1975. Dyson and Lenard proved 8 years earlier that without it, the stone would not exist. You look at it more closely. Its color, whether gray or brown or speckled, comes from the way light interacts with the electron configurations of the minerals inside it. Those configurations, the way silicon and oxygen and aluminum and iron arrange their electrons, are dictated by the periodic table. The periodic table exists because electron shells close. The shells close because each quantum state can hold at most 1 electron. The stone's color, its texture, the minerals it contains, are all readouts of the exclusion principle applied to atoms of different sizes. You hold it up against the night sky. Some of the points of light you see are white dwarfs, exclusion principle objects supported against gravitational collapse by electron degeneracy pressure, with a maximum mass of 1.44 solar masses. Some are neutron stars supported by neutron degeneracy pressure. Some, unseen, are black holes, the remnants of collapses where even the exclusion principle could not hold. You think about the space between you and those stars. Every cubic centimeter of that space, according to the best quantum field theory humanity has ever produced, should contain a vacuum energy density that, if you trusted the calculation, would curve the universe so tightly it could not reach the moon. The calculation has been checked. The mathematics is not in dispute. The answer is off by 120 orders of magnitude. The stone works. The space around it does not. Both answers come from the same physics. Both use the same mathematical framework, relativistic quantum field theory, the framework that Pauli helped build, the framework that connects the speed of light to the exclusion principle, to the stability of matter, to the energy of the vacuum. One side of that framework, the matter side, is the most successful physical theory ever constructed. It predicts the magnetic moment of the electron to better than 1 part in a trillion. It explains every element in the periodic table, every chemical bond, every stellar remnant, up to and including the boundary where matter gives way to a black hole. The other side of that framework, the vacuum side, produces a number that is wrong by a factor so large that calling it wrong barely captures what has happened. It is not a prediction that missed by a little. It is a prediction that missed by everything. And the people who understand both sides of this, the theoretical physicists who work at the intersection of quantum field theory and gravity, have been staring at this for 100 years and they do not know why. Pauli saw it first. He computed the vacuum energy in the 1920s, recognized that the gravitational consequences were nonsensical, and turned away. He did not solve the problem. He buried it. He spent the rest of his life publishing the exclusion principle, proving the spin statistics theorem, winning the Nobel Prize, being the conscience of physics, searching for the deeper pattern in his correspondence with Jung, dying in room 137. And the calculation he turned away from is still sitting there, unsolved, unanswered, the largest quantitative discrepancy in the history of science. The next time you pick up a stone, hold it for a moment. Feel its weight. Feel its refusal to compress. That refusal is the exclusion principle. That weight is gravity. Both are well understood, well tested, well confirmed aspects of the same physical world. But when you ask why the principle holds, the answer requires relativity, and nobody can explain intuitively why. When you ask what the vacuum between the stone and the stars should weigh, the answer is off by 120 orders of magnitude, and nobody knows why. When you ask whether the same equations can really be both spectacularly right about matter and spectacularly wrong about empty space, the answer is that they are, and nobody knows how. Wolfgang Pauli, born April 25, 1900, in Vienna, godson of Ernst Mach, pupil of Sommerfeld, author at 21 of the Definitive Review of General Relativity, proposer at 24 of the Exclusion Principle, suppressor at 25 of the correct interpretation of electron spin, prover at 40 of the spin statistics theorem, winner at 45 of the Nobel Prize, patient in his 30s of Carl Jung, correspondent for decades on the meaning of dreams and the fine structure constant and the pattern underneath the patterns, and finder in his 20s of a calculation about empty space so broken it predicted a universe smaller than the distance to the moon. He published the principle. He buried the calculation. The principle holds up every atom in your body. The calculation remains the worst prediction in the history of physics. The stone in your hand is his. The space around it is his too. One works, one does not. Both come from the same place. And the reason, 100 years later, is still not known. Dyson later reflected on the stability of matter proof in a way that reveals something about how he thought about physics. In a lecture he gave at the American Mathematical Society, he described the problem as one of the great intellectual scandals of 20th century physics. The fact that for 40 years after quantum mechanics was formulated, nobody had proved that the theory predicted stable matter. Everyone assumed it did. Everyone used quantum mechanics to calculate the properties of atoms and molecules and solids. But nobody had actually proved with mathematical rigor that the theory did not predict that a sufficiently large collection of atoms would collapse. The assumption was so deeply embedded that most physicists did not even recognize it as an assumption. They had calculated the ground state of hydrogen. They had calculated the ground state of helium. They had computed molecular binding energies and crystal lattice energies, and the properties of the Fermi gas. All of these calculations gave sensible, finite, well-behaved answers. But none of them constituted a proof that the general n-body problem was stable. The individual calculations worked because the individual systems were small. The question was whether the success scaled. Dyson's own words from a 1967 lecture were characteristically blunt. He said that the situation was embarrassing because physics had been using quantum mechanics for 40 years to explain the properties of matter, and the whole time the logical foundation for this explanation had been missing. The Dyson-Lenard proof was not a theoretical curiosity. It was retroactive justification for 4 decades of applied quantum mechanics. And the proof was hard, genuinely hard, not pedagogically hard in the way that a textbook derivation might be long but straightforward. Hard in the sense that it required new mathematical ideas, and new inequalities and arguments that strained the techniques available at the time. Lenard later said that the proof was the most difficult piece of mathematical analysis he had ever been involved with. The two of them worked on it for over a year. The paper, when it appeared, was dense even by the standards of the Journal of Mathematical Physics. This is worth dwelling on because it tells you something important about the exclusion principle. The principle itself is simple. No two fermions in the same state. You can write it in one sentence, but proving that this simple rule is sufficient to guarantee the stability of bulk matter. Matter containing 10 to the 23rd particles or more required some of the most sophisticated mathematics of its era. The gap between the simplicity of the principle and the difficulty of its consequences is itself a kind of mystery. Simple rules can have enormously complex implications, and the exclusion principle is perhaps the most extreme example of this in all of physics. There is one more thread I want to pull before I bring this to a close, and it concerns the relationship between Pauli and Einstein. They were not close friends in the way that Pauli and Bohr were, or Pauli and Heisenberg. Their relationship was more like that of two chess players who respected each other's game, but played very differently. Einstein was a visual thinker, a man of thought experiments and physical pictures. Pauli was an algebraic thinker, a man of symmetries and mathematical structures. Einstein trusted his intuition and was sometimes wrong. Pauli distrusted everyone's intuition, including his own, and was almost never wrong about matters of physics. But the two of them were connected by the exclusion principle in a way that neither fully appreciated during their lifetimes. Einstein's special relativity, published in 1905, provided the framework. Pauli's exclusion principle, proposed in 1925, provided the rule. The spin statistics theorem, proved by Pauli in 1940, connected them. And the connection says that without Einstein's relativity, there is no proof that Pauli's rule must hold. The solidity of matter is at bottom a consequence of the constancy of the speed of light. Einstein knew this in the way that Einstein knew most things, intuitively and ahead of the mathematics. In his speech at Pauli's Nobel banquet in 1945, he described Pauli not merely as a brilliant physicist, but as his intellectual successor. The abdication of a king, Pauli called it. But it was not abdication. It was recognition. Einstein was saying that the torch had passed to a man who understood the deepest structures of the physical world, structures that Einstein himself had helped create, but that Pauli had been the one to name and prove. Pauli outlived Einstein by only 3 years. Einstein died on April 18, 1955, at Princeton. Pauli died on December 15, 1958, in Zurich. They are buried on different continents, but the physics they built is one continuous structure, from the Lorentz transformations to the spin statistics theorem, to the stability of matter, to the stone in your hand.